Please go ahead.
Okay, thank you. So thank you all for attending to this final workshop of the project. Now I will introduce these activities. I'm David Pampliega from Schneider Electric, and we are coordinating one of the demonstrators of the project. It's about adaptive models for with behavior prediction with power systems stabilizers. We are addressing several problems in this demonstration. The first one for TSO, the aim is to enable them for having a higher transfer capacity and stability, which will be very useful in scenarios with a higher penetration of renewables. This is like that because the modes in this kind of scenarios will change more frequently, and then the power system will be more vulnerable against the different fluctuations of the generation of these renewable resources. We will also address some issues for plant owners. First of all, about the reduction of OPEX for their equipment, because as we will have some oscillations dampened, the equipment will work under less stressing conditions. Okay, so allowing to reduce this operating cost. And also the plant owners will benefit because their system will be more prepared against future grid requirements that could be in place. And also as a general objective or issue addressed is the general improvement or facilitation of a higher penetration of renewables, facilitating to the consumers, to the owners of the system, of the plants, and different actors in the overall supply chain. Because of that, because of these problems that we introduced, we have defined several objectives in this demonstration. First one is to build a grid model in order to represent the behavior of the grid with synchronous generations. And the next one will be to develop tools and services to allow improving the performance of synchronous generators and to mitigate frequency excursions in order to damp low frequency oscillations that could happen after a disturbance. You can see in this slide as many organizations are involved. It's a great mix between technology providers, research organizations, and end users like the plant owners or even transmission system operators from different countries in Europe. So this allows us to have the right balance and the right skills in order to build a solution with the aim of allowing this higher share of renewables thanks to the tuning of power system stabilizers. So the main challenge that we are addressing is to achieve an adaptive PSS tuning. This is like that because normally PSS are based on fixed parameters that are not updated regularly. So normally the operator of the PSS will be able to change the parameters, but they will do that in a manual way based on on their know-how or the experience in operating PSS and so on. But it will not be a real-time application. In this case, we are targeting to obtain an adaptive PSS tuning that will be updated in real time based on the conditions of the grid. So because of that, we are proposing a combination of gray box and black box models. The gray box model will allow to identify the main modes of the system during a training phase that will be performed offline because it will be a time-consuming process. And then we will have a black box model that by using machine learning techniques and by getting the output from the gray box model and also real-time measurements from remote terminal units and facial measurement units will allow to find the current mode of the system at every instant. So you can see in the diagram below how this schema will be put in place. So we have this gray box model with the network model and getting the low frequency oscillation database as an input to the black box model, getting also the data from the wide area measurement system coming from remote terminal units or PMUs, and then it will allow to adjust the PSS parameters, okay, to actuate over the exciter or the governor of the generators. The demonstration architecture in the site that we have implemented is depicted in this slide. We have a controller box, okay, which is the large section here in white, which contains this controller, which implements the black box model algorithm, and also a remote terminal unit acting as a communication gateway with the systems from the area of influence of the plant in which we are implementing this technology, and also communicating with the AVR, getting all the relevant data from its behavior, and also allowing to operate it based on the commands, instructions originating at the controller. So in this case, we will have, as mentioned, some remote measurements spread all over the area of influence of the plant in which we are implementing the system. So normally this will come from the transmission grid through the remote terminal units that they have deployed. So in this case, we have enabled the communication using IC104 protocol to the RTU. So they are providing from the transmission grid all the data that it's of interest based on the needs. Normally are voltages, currents, powers that we are getting to process in the black box model algorithm. Then we have the AVR, in which there is a bidirectional communication, because we are getting measurements from the AVR and also all the settings, parameters that have been defined in the AVR. And the controller, again, bidirectional communication, because the controller will receive all the data from the AVR and from the transmission grid, will perform the calculations, and then will send the information back to the RTU and then to the AVR in the end. Finally, in the architecture, we can also see the PMU system that we have been using for monitoring purposes and to confirm the different hypotheses of the models. In this case, there are two PMUs deployed, one in the transmission grid and another one in the power plant. So now, just to go into real pictures of the demonstration site, which is a cogeneration power plant in Bulgaria, which is called Cogen. They have two generators of 3 megawatts each, and they are connected to the transmission grid of Bulgaria. So you can see a real picture of the AVR in one of the gensets on the left. Then we see the control box, which has the controller and the RTU here in the middle. And then finally the PMU that has been used in this demonstrator. Just to mention a few of key achievement results. We have achieved a performance higher than 92%. That was above the initial expectations, because normally when we define the expectations, we made use of historical data. So we were expecting a performance of about 85%. So finally, when we were able to deploy the system and test with real-time data and actual data coming from the field, it was possible to exceed the performance. Also, the PSS performance with adaptive tuning was analyzed with respect to the deviation of the active power. In this case, we achieved that the deviation was reduced about 5%. Again, we expected to achieve 1% reduction based on historical data. So we were able to exceed the initial expectations that we had when we started to work in this demonstration. Also, it was very useful, this demonstration, because we were able to validate that the simulations in a hybrid environment in hardware in the loop, like it was presented in previous presentation by List, were very useful to and consistent with the experiences that we obtain in the field. So it served to validate this way of working as a successful one in order to develop and testing different strategies in the lab to then be able to apply the most successful ones in the field without having to do a lot of experimentation in the field that normally is much more costly and less optimal to be done than in the lab. So some recommendations with respect to technology, in case that higher levels of accuracy were required or needed, we anticipated that transfer learning would be a potential solution for improving the prediction models without needing to go back and retrain the models from scratch from the very beginning. Then with respect to policy, as already introduced at the beginning, this adaptive PSS tuning approach will allow the plant owners to be ready to comply with future requirements. And with respect to regulation, the logging and fine-tuning capabilities that we will have with this system that we have deployed will facilitate to fulfill the different regulations that are put in force also in the future. So we will give both the system operators and the plant owners with tools to comply and to log with respect to the regulations that may be required to them. And that's it. I'm now open to reply to any question that you may have, in case you're interested in.
Thank you very much, David, but also Professor Petro. So you can see the final two presentations representing the tool and house simulation. So is there any burning question before we can have some general discussion among the speakers?